here. So another biggest source for organic chemistry, organic compounds are, one is mine, I just said, petroleum. Another one, animal body, plants, animal kingdom. Plants belong to animal, right? No, living creatures. This is living creature. All the compounds that we get from our body mostly are organic. There are some, of course, inorganic, but trace amount. Mostly are organic compounds in our body. And another criteria for organic chemical is, what is the most abundant element you get in organic compounds? Carbon. Yes, they should have a carbon chain, carbon backbone. It should have a carbon backbone. So some student then answer, oh, sir, why carbon dioxide is not, carbon monoxide, carbon dioxide is not organic? No, it doesn't have the carbon backbone. It has only one carbon, right? Carbon backbone. And also organic molecules mostly are volatile, mostly. And it is most, to some extent, is non-polar. There, of course, there are some polar. You already have submitted one lab report. You are supposed to have, know this. Anyway, anyone else is joining here? No. So what's the time now? All right, I think we can start. I hope those who are coming here, we are at, let me put it on the chat. Oh, food, oh, carbon. You see, you already almost got the answer, but you didn't tell me. I didn't see the chat box. You should have just unmute yourself and talk. We are at B210. Lecture room. Right, let me start the projector first. One 7 to 16 12 47. So what are we up to today? What are we going to learn? What are we going to learn? Have you seen Morrison Boyd or McCurry book? It is just one small book for organic chemistry. You haven't seen the finer, you haven't seen the other books. Yeah, you know that this is different, right? Organic chemistry is a very big subject. You know from the sources also. Okay, so we are here and oh, you can see, right? I don't want to show you now. That will come later. Okay, so previously, last class, we were here. Nomenclature, we have done the nomenclature. We have done the how to assign highest or lowest number to find out, because the name, only the naming does not, only the naming does not give us the, on the structure of the atom. Only the name does not justify the structure of the atom in the name, because there are cis and trans conformation, and there is cis and trans itself does not do the justice for when the bigger molecular substituted. All right, when bigger molecular substituted, so we have to go for E and Z transformation. So E and Z, cis and trans, we know, right? Cis and trans, we know when there is a double bond, when there is a double bond here between carbon and carbon, and then two similar groups, substituted group, are on the same side of the double bond with the two different, right? Two different carbons. So here is one carbon. Here is one carbon, and here is one carbon, here is another carbon, and there is a double bond between them. So there are two groups. There are two groups. R represents one group. These are, so here two different groups are on the other side. On the other side. So if that is on the other side, it is a trans. It is on the same side, not on the same carbon, yeah? Not on the same carbon, two different carbon, but on the same side of the double bond, it will be cis. And what does the cis and trans do? Actually, I was talking a bit yesterday, is it? I think yesterday I was talking. Oh no, Saturday. I don't know if you have seen it or not. This cis transformation isomerism actually works a huge amount for our vision, that I'm looking at you or you can see me, is just because of the cis and trans formation. This is the beta carotene. You can find it from carrot a lot, palm oil as well. So this beta carotene is a precursor of vitamin A. I have talked about it. I'll not go in detail, but just to inform you what I have taught on Saturday. So this beta carotene is broken or hydrolyzed to become vitamin A. This vitamin A is not directly related or responsible for us to. Have you heard that vitamin A is good for eye health? How many of you have heard that vitamin A is good for eye health? None? Have you heard? No. Seriously. Vitamin A is good for eye health, and you can find a lot in carrot, veggies, small fish, and so on. So on. I'm not a dietitian, so I cannot tell you exactly, but as much as I know. And this vitamin A is not directly related. It will transform to cis retina. Now tell me, which one is easy to be transformed? Cis or trans? Cis or trans? This will be cis. Bond. Let us say that here, here there is a double bond, and this group, and this group on the same side of the carbon. There is a one carbon here, one carbon there. CH3 is here, and then it has CH3OH. Sorry, CH2OH. So these two groups on the same side, right? When it is becoming other, okay, let me do that. So this one, you tell me now, which one is easier? It is easier to be on the same side, CH3 and CH2OH, or it is easier to go to this side. Which one is easy for this compound to be formed? Which one is easy to be formed? My question is not correct. No? My question Do you understand what is my question? No. Because the previous thing I didn't talk, and the previous thing is on the Thursday actually we discussed. That means you have not gone through any of the lecture or also haven't seen the things. Because there are 6 strands, when there is a double bond, better that I do it here, right? So when there is a double bond, let's say I do it here, carbon-carbon double bond, and there is a carbon-carbon single bond. Of course, each of the carbon has other bonding along with it or on it. It has 3 bonds. It has also 3 other things attached to it. So which one? This is carbon. This is carbon. Which one is easy to rotate? A or B? Let's say this is A. This is A. And this is B. Which one is easy to rotate? A or B? A. B. See, 50-50. Now you have to vote so that I know which one is winning, A or B. I got one A, one B. The rest, what? Which one is easy to rotate? B, because B has one single bond. So if like this, 2 bonds are attached to how, I mean, you cannot rotate, it is going to break. But if there is one single bond, it is easy to rotate, right? So that is why when there is a cis or transformation, when there are cis and transformation, this is when there is a cis, it is not going to go to trans. It cannot, because it is already 2 bonds are holding it, and it cannot just rotate and go to trans. However, it is easy for it to form cis bonding because it can just attach to the same side. It does not have to have extra energy to go to the opposite side, right? So that is why cis is it. And then cis, it becomes vitamin A when it is in the cis formation. We call it cis retinal, right? We call it cis retinal with a little bit of photon, as low as 5 photons only. Only 5 photons can cause one molecule to transform to trans. This 5 photon can give enough energy for this cis to go to trans. Here, it is becoming trans, and when it is becoming trans, it is getting straighter. Can anybody tell me why? When it is trans, it is becoming straight. Little bit straightened. Why? When there is cis on the same side, right? There, on the same side, they are having some steric hindrance. So, to minimize the steric hindrance, they bend a bit. And that is why bending. But when they are having trans, there is no steric hindrance. So they do not feel that pressure, the steric hindrance, that becomes straight. And that is the mechanism for us to see, actually, the light. See. Because of this straight, it can penetrate the membrane of our eye. There are 2 cones, right? Rod and cone. There are 2 types of nerve in our cell, actually, in our eyes, rod. So this is in the rod. It penetrates the cell wall and allow the carbon and the calcium ion to be triggered. Calcium ion is triggered at that time. And then it sends the signal to brain that, okay, this is a white, this is a black, this is a round object, this is a not round. So that is how we see. Do you think that the thing I'm seeing it is going through a tube from my eyes to the brain? There is no tube. There's just a nerve, right? There's this nerve. So rod and cones processing. It is big, small, black, white, and then another thing is, okay, since we are talking about the calcium ion, let me just inform you that lead. Have you heard that lead is bad for health? Lead, Pb. Lead is bad for health. Have you heard? Carcinogenic, right? Heavy metal, right? Lead is. So lead, it actually mimics as a calcium ion in our body, and it is stored, and that is why lead is very bad. It cannot be removed from our body. Okay, since we are here. Now we saw the cis and trans, and then cis and trans cannot be justified only by cis and trans because it does not the similar molecule or same type of molecules on the both side, or if it is a big one, a small one, then what do you do? We know denote as a ENG formation, right? ENZ or ENZ formation when there is a same side of the highest group or highest number molecular group on the same side. We call it Z on the same side. So Z will be cis, right? Z will be cis, and E is trans on the opposite side. But what does this high and low means? Based on the molecular number or molecular weight of the groups will be attached to here. Yes, so here we see that this is Z, this is E, because we see that CH3, chlorine, although the CH3 on the same side, so anybody easily can call it 6, let's say that there are some other compound here. So 6 2-methyl, 2,3-dimethyl, chloro something, butene, propene, something, right? We can call it. But if it is a longer molecule, we can call it as an E. Right? We can call it E because on this CH3, although they are same side, there's on chlorine. Chlorine is higher. The molecular mass of chlorine is what? 35. Right? 35. CH3, what is the molecular weight of CH3? 12 carbon, 12 plus hydrogen is 17. So 17 here, and this is 35 molecular mass. It is easy. We have seen it from the periodic table, right? On the periodic table, we have seen the molecular mass of chlorine and or any other hydrogen, chlorine, carbon, nitrogen, everything. So here, chlorine is high molecular mass, atomic mass, and this CH3 is highest among these. So you can ask that, why do you say about this CH3? Why not you are considering this CH3? Right? So you can say that, okay, true question is okay, but the problem is for cis and trans or E and Z, it has to be on two different carbon, either side of the double bond, not on the same carbon. It has to be double bond, either side of the double bond, right? So that's why this CH3 and this chlorine, it does not matter where it is, as long as this is one high on this carbon and there is another high on this carbon, this matter. And the opposite is true. When there is opposite thing, that is the chlorine on other carbon and CH3 on the other carbon, but on the same side, if we consider there is a plane, right? There is a plane through there, so that this CH3 and chlorine is one side, and there is a plane on this side, the chlorine and CH3 on the other side. So this is a E and Z on the same side. All right. So yeah, alkene stability we are studying. Alkene stability, of course, there will be steric hindrance that was talking, and because of steric hindrance, this it is bending. It was bent for cis retinol, and it happens the stability of we are talking about stability that the more substitution, the more stable it is. The more substitution, the more stable this alkene is. What do you understand from this statement? Online, how many of us online? Let me check. Oh, Audrey, sorry, you did not, I mean, I forgot to start sharing. But yeah, luckily I checked. You should have talked, you know. Sorry, yeah, what? Veran, you're asking something? Yeah, tomorrow. Huh? When? Which one? If tomorrow, then next week. Why? You have something else? Yeah. Test, anything else? But you have 1 week to do. 3 of you in the group. I think you can manage it. And yeah, another thing I was okay. So now, hello. Yeah, I will give you after half an hour. I will give you 5 minutes to break so you can talk. Okay, so alkene stability. I was talking about the alkene stability. The more substitution it is, more stable it is, right? What do you understand from this statement? What do you understand from this statement? The more substitution, the more stable. Anyone? Yeah. What is this statements tell you? Looking at the slide, what does it tell you? More substitution, more stable. Substitution by whom, with whom, to whom, at where, what? If I ask this question, how can you answer? Substitution by whom? Any other alkyl group, okay, substitution at the carbon on the either side of a double bond. Okay. Carbon, how many bond carbon can have? 4. This is very important. Remember that carbon can have only 4 bonds, not more. It can have less than that, but it will not be stable, right? Because the octet is not filled in that way. So 4 bonds, and then 2 bonds between carbon and carbon. So another 2 is available for carbon. So these 2 bonds will be bonded with some other group, other element, right? Either hydrogen or fluorine or bromine or anything else. And then this will be replaced by alkyl group. And each of these double bonded carbon can have maximum of 4 other substituted group. That's alkyl group. And the more the substitution, that means if 4 of them is substituted, all of them are substituted, that is tetrasubstituted, and this is very stable. This is very stable, and this is very stable. For this case, you see that 4 of them are substituted, so 4 of them are here. This is the most stable. What is stability? What does it mean? Do I need to point you out? No. Okay. So my question to everyone: what is stability? What does stability mean to you, or what do you understand from this? The stability. Yeah, I'm asking. What is stability? Veron? Yeah, what does stability mean? Stability means not stable. Right? No. Jonathan, nobody's talking. What is stability then? Right? Yes, they are not really reacting, but they are not getting attacked easily. Now, okay, is that okay? Gabriel is okay? Okay. So my question now, that why they are not getting attacked? What is happening that they are not getting attacked? There is double bond. Previously, last class, I told you that when there is double bond, they get more susceptible to attack, right? Because there is a pi electron there. So why are they not getting attacked? Huh? Sorry? Yeah. What makes them stable? This is, huh? Sorry, what? What is that? Why they are getting more stable? Huh? Octet rule. Yeah, there is, everybody is octet filled up. But the thing is, there is a double bond here. Double bond means 2 extra electron. And double bond easy to break. We have seen it. Double bond easy to break. All the reaction is happening in the double bond because when there is a single bond, carbon to carbon single, that is the alkane, rarely there is any reaction. If there is a reaction, you have to provide heat or UV light, many things, right? But for this case, double bond, you have seen that you don't need anything. You just need to add, there will be reaction. But for this case, it is becoming more and more stable. This is the octet filled up as well. This is also octet. Here all are octet filled up. Here everything octet filled up. Here everything octet filled up. But here as well octet filled up. But this is more stable than this. What is the reason? The interesting thing is science deal with reason, right? Science, we deal with reason. We want to find out the core problem where it is more makes more sense. Or we want to search, go deep into that, why it is happening. We don't have to go all these like methane, ethane, propane, butane, pentane, everything. We just need to see what is the purpose or what is the reason so that we can find the explanation for everything, right? So that is what is the reason that it is happening here. Because one is their hyperconjugation. Hyperconjugation is there. Second is this S character is increasing because more SP character is in P is there. When more carbon is attaching there, more hydrogen is coming. That means more S is coming. S character, most S orbital is coming there, right? And also, since this is big, R is bigger than hydrogen, of course. Any CH3, even CH3 is bigger. CH3 is bigger. All R are bigger. So the other, those who are supposed to attack, there is a name for this who will go to attack. We'll see it next slide. They have less chance to get into that pi bond, right? So they are getting impeded. Okay. But at the end, the reason for this are not quite clear yet. We all do not know 100% of what is the reason. It was supposed to be, sometimes it is counterintuitive, you know. When there are more CH3 group bulk, that becomes heavier. So they want to break free and then get their, settle there. But instead, it is getting more stable. That's the interesting thing. So there are some areas of, uncertain or unknown thing is there that we do not really know what is going to happen. Happening. Of course, if we could travel into that molecular or atomic level, if you or me could travel to that electron orbital, probably we would see that what is really happening. But all these things, the orbital, electron, neutron, proton, how can we see that? Do you know how do we see that? Any idea how do you see that? If I give you a hydrogen atom and I ask you to see the electron and neutron, how can you see that? What microscope will you use to see? The smaller thing we see through microscope, right? So under what microscope do you put the hydrogen atom and see the electron and proton and neutron and all those things? What? Telescope? Sorry? Telescope. Okay, one answer we have gotten, telescope. You cannot see any atom. Telescope is to see the meteors and the outer space. You cannot see an atom. All these electrons that we are talking about is based on our imagination and based on the calculation. Electron microscope cannot see the electrons. It takes the help of the electron to visualize the smaller particles, but a smaller part, but it does not see the atom. We do not have the technology yet to see an atom. So all these orbitals, electrons, neutrons that we are talking about is based our imagination and of course through some calculation. All right. So that's why imagination is very important. But imagination is important. Don't mistake it as daydreaming. Right? Don't just sit and dream like this. It's not imagination. Okay. Okay. So now we are moving into the reaction that heats of hydrogenation. Again, we are going to the counterintuitive thing. Just now we said that when there is a for substitution, it is more stable, right? That means when there is a carbon-carbon single bond, carbon-carbon single bond here, carbon-carbon single bond, that means ethane. Let's say it is an ethane, right? Carbon has 3 bonds to each other, carbon and carbon, and is an ethane. So what does this line mean to you? I'm saying that is a carbon and carbon ethane, right? Methane, ethane. So these are all hydrogen, right? This represents hydrogen, that hydrogen is attached. It takes time for me to write, that's why I'm not writing, but you know that is hydrogen, it is hydrogen there, right? So ethane, if I want to react this ethane with hydrogen, I put some more hydrogen, what will happen? No reaction, because it does not have any other option for this carbon to take up any more hydrogen. It's totally complete, it's full. But if this is a double bond, carbon-carbon double bond, right? It's carbon-carbon double bond, just like this. Here is an alkene. It has hydrogen here, all hydrogen here. But it has an option to break this one bond, one pi bond, not the sigma one. The pi bond is breaking and then taking up 2 more hydrogen, right? It has an option. And it is quite fast. It is without much, what do you call it, try. You can get it because it is very much reactive. Alkene is very much reactive. So hydrogen, you just put in the hydrogen, there will be a reaction, but to make the reaction faster, of course, we have to use some catalyst, that is the platinum, palladium, nickel, and iron, all those things we can start. Now, the thing is, what is that? I want to say that. Oh, yeah. So if I add hydrogen, there, okay, the more heat comes out. What does it tell you? Let's say that I am, how do I put it? A firecracker, this big firecracker, you play with it, you set the fire, and it becomes making a very loud noise, right? Firecracker will make a loud noise. I give to one Timon on to Veron, and his one is making more noise or sound than Veron one. What does it tell you? That is more powerful. That means more reaction is going on to that, right? So that means the more heat it comes out from the reaction, it means it is going to be more stable. It releases more heat to become more cooled down, and then it is more stable. It's going to be more stable, the product. Right? So the heat comes out. It is not only that all the C double bond of carbon-carbon double bond will exactly give you the same heat. It depends on what is the chain length, what is the other compounds there, other groups attached to there. All these things will be related for it to be stable or not, whether it is more stable or less stable, right? So yeah, so this will give us an stability factor of the stability. And how it is happening, the reaction is happening. We know that in that double bond, there is more electrons, right? More electrons. Is it okay if I call there is more electrons in the double bond? So in the double bond, there are more electrons. So who will be attracted to the electron? You have 5 smartphones. Who will be attracted to get one? Another has 5 as well. Will he be attracted to you? No. I do not have 5. I will be attracted to get one from you, right? So those who are not having electron, of course, they will be more attracted to you. But in this chemical, terms, we do not call them they have less or more. We call them there are some specific name. There is one is electrophile, one is nucleophile. Electrophile, philic. We know the phobic, right? Phobia, we know. Phobia means fear. Philic means we are attracted to that. So electrophilic means is attracted to electrons. Nucleophilic means it's attracted to nucleus. So when there is a reaction, of course, an electrophile will come here and attack or be attracted to these electrons because there is 2 electrons to take up from here. And those 2 electrons are loosely bound, the pi electrons. So it is the best choice. The sigma bonds are too strong and it is not available. It is not all the way, circling all the around. So it is available, right? The pi bond. So the electrophile will come here and attack. And that is how the electrophilic addition reaction will start. So just now I was talking about electrophile and nucleophile is here. How does the reaction start? The reaction starts not from the electrophile first, okay, but from the electrons. So this one is the electrophile. Is already written electrophile here, hydrogen bromide or hydrobromic acid, right? It is an electrophile. That means it loves electron, but it is not originating from itself. When it comes nearer to this what do you call it? This cloud of electron, they are getting tensed. The hydrogen and bromine getting tensed and getting separated first. So that is the starting of the mechanism. So they are getting broken up first, and then the hydrogen becomes positively charged. It's become positively charged. It becomes negatively charged because this electron here by this arrow. What does it mean? This arrow. What does it mean? This arrow. Sorry. What does this arrow mean? Here there is a lot of electrons, right? In this, this is a pi bond, p orbital. This is a p orbital is shown in that way. So there is a lot of 2 electrons, available electron. When hydrogen bromide is coming this close to that, hydrogen is getting attracted by these 2 electrons here. And that is how the separation starts from hydrogen bromide, hydrobromic acid, right? So the bromine, of course, it is more electronegative than hydrogen. So it will take the electron, withdraw the electron from the double bond. They are bonding in this way, hydrogen and bromine. And when it is coming near to that, so they are getting a bit more tension, like this, a big tension. The bond is getting elongated. After some time, the bond is broken, right? So bromine is taking the both electrons towards it because it's more electronegative, and hydrogen is becoming positive. Of course, it will feel positive because the electron has been taken. So when it's become feeling positive, it will be attracted to this excess of electron it has, and then it is getting attracted. It is getting attracted to this pi bond, the electrons in pi bond, and after some time, it is not directly. I mean, it is not like that happening the reaction. This is the difference between organic and inorganic chemistry as well. In organic chemistry, the reaction is very fast, one step, right? For organic chemistry, it is slow and stepwise reaction. Later on, I will show you how the reaction mechanism is happening for SN1, SN2, probably not today. SN1, SN2 reaction is happening, and also how the reaction that were occurring during the lab, you did it here last week for experiment 4. So how this reaction is occurring. So this, I mean, after they become separated, there is a double intermediate species. It is called the intermediate species. So they are there for some time. Carbon become positively charged, and then hydrogen is going to another carbon, and then again this bromine, because it doesn't have anywhere else to go, so it's coming and getting attached to this hydrogen. Where is it? Yeah, it will go and come to this hydrogen later on. Yes, yeah, it is shown. All right. So this is called the mechanism, and of course hydrogen iodide will be reacting faster than hydrogen chloride. Can tell me why? Hydrogen iodide will react faster than hydrogen chloride, hydrochloric acid, then hydrobromic, of course, hydrofluoric acid. Why? Sorry? Of? No, electronegativity of fluorine is higher. Yeah, fluorine is the highest electronegativity. So why it is so? Why is in this sequence that hydrogen iodide will react faster or higher or more than others? Why? Huh? Which one is more stable? No. If it is stable, then it is not going to do the reaction. Hydrogen fluoride is more stable. Hydrogen iodide is bigger molecule, right? So iodine is bigger, and then hydrogen is, so they have already a big length, a bond length. So it is easy to get separated, right? So I'm not sure whether should I talk, I tell you, but when you have a relation, either to your friends, family, or anyone, when the relation is close, you know, it's not easy to break, but if it's getting strained, then yeah, it's easy to break. So this is our human relation as well, because we are made of chemicals anyway. Okay, so electrophilic orientation of this reaction. Interesting thing is this carbon, this hydrogen here, this bromine, right? This bromine, it is, I'm showing that, let's say, denote this carbon as 1, this carbon as 2. Right? So I'm telling that this bromine is going to number 1 carbon, and then hydrogen is going to number 2 carbon. I'm showing it here, right? 1 and 2. Why this bromine shouldn't go to this number 2? Why this bromine shouldn't go to this number 2? I mean, is it just for the sake of showing it, or it is actually something is happening there? Okay. Is it? I mean, is it a mistake, or it is actually the same thing? Important thing that I'm showing it. It is an important thing that I'm showing because this is called a regio-specific reaction. Regio-specific means region, right? The site is specific. Region is. It is exactly to this carbon it will happen. It will exactly to this carbon it will happen. It is this type of reaction is important because many of the time we do this reaction in the industrial level to produce more product, right? So this is actually a Markovnikov rule, a Russian scientist, chemist, in early 90s, probably 80s, 18s. So he came out with this idea, this Markovnikov rule, that hydrogen and chlorine, if any halohydrine is reacting to this double bond or alkene, the product will always be this similar type. It is not like lump sum, hydrogen is going here or carbon is going here. No, hydrogen specifically will go to this carbon, the chlorine or fluorine will specifically to that carbon. That is called regio-specific, and this is called Markovnikov rule. So the rule is this type of reaction, the hydrogen, right? This hydrogen from this hydrochloric acid, or let's say it's hydrobromic, hydroiodic. We are not talking about hydrofluoric, yeah? Hydrofluoric is different and it takes some other consideration. So we will not talk about the hydrofluoric. I don't want to make the things complicated here. So hydrochloric, hydrofluoric, hydroiodic or bromic, these all things, the hydrogen will go to the carbon which has more hydrogen already attached. This carbon we see, this is number 2, this is number 1 carbon. It already has 2 hydrogen. And for this 1 carbon, it has none. Yeah, it has hydrogen, but it is directly connected to carbon, not to hydrogen. But this carbon is directly related to connected to hydrogen. So the hydrogen will go more to the carbon which has more hydrogen already, and the other thing will go to the other carbon. So this is called Markovnikov rule. You can read the Markovnikov rule, of course, there are quite many ways you can describe it, but I love this number 3rd and number 4th one. Number 3rd is the hydrogen attached to the carbon with most hydrogen already there to the carbon, right? Or if you even cannot remember this, just remember that the rich get richer. I think you can remember that way. But when there is the Markovnikov rule, there is another rule that is called anti-Markovnikov rule, and we will see it later on. So how this reaction is occurring? So we have already seen that. We have already seen that the tertiary carbocation is much more stable, right? It is more stable when the carbon all substituted, because we know why. So what is happening? The reaction is that the hydrogen and chlorine or hydrochloric acid hydrochloric acid, yes, yeah. It is getting tensed, and then it is getting elongated. Hydrogen and chloride getting partially charged. It is not getting just like human nature. It is not direct. It's not breaking that way. First, they feel the tension, then they partially become charged. Hydrogen become partially positive. Chlorine becomes partially negative, and then this partially positive hydrogen is getting attached to this double bonded pi bonds electrons, and then the pi bond electrons, it is filling the partially positive charge. That is the intermediate three substituted carbocation forming, and then the final product is put in. So why this type product is possible? Because of this carbocation. If this way it forms, right? If this way it forms, the carbocation is forming here is more substituted than this way it forms. It has two substituted carbocation, then here, if this carbon does not have any substitution on it, it is only hydrogen it has, right? So this carbocation will be less stable, of course, than this carbocation. This is the first intermediate. Okay. This is the first intermediate, and then this is second the below one. Intermediate, and this is second intermediate. The first intermediate is much stable because it has most substituted carbon. Second one doesn't have. Okay, so that is why this type of product is more stable. Addition of halogen to alkene is quite easy actually. The halogen will be attached to the either side. But the whole scenario changes if tetrachloride is to this. We are going to the reaction now and more to the stereochemistry, and then okay. So after this, so halogen we are adding after this slide. I'm going to give you a few minutes. So halogen is attached to this double bond, and since this halogen is X2, let's say it's a chlorine 2 chloride, right? Or 2 bromide or 2 iodide. Or 2 iodide, anything. So this is chlorine and chlorine atom. Of course, there is no specification it needed. It will just add it to these two double bond, either side of the double bond to the two carbons. But if the whole thing will be changed and it does not have an excess of energy, so it is just going to somehow it will be attached. So when somehow is attached, it is going to be cis formation. It's going to be cis formation because cis formation does not need much energy to be attached or to be formed. But for trans, we need more energy to produce the trans. And then trans will be formed if you force it to go to the trans. How do you force it? We make it stiff so that it does not have the degree of rotation, or it does not have that liberty to rotate. So we are forcing, okay, you go there, you go there. How? We are packing it with something else. That packing is this carbon tetrachloride. Where is my cursor? Yeah. This packing is this carbon tetrachloride. Carbon tetrachloride is a solvent and is organic solvent, and it is non-polar in nature. It is not polar, carbon tetrachloride. So in presence of carbon tetrachloride, right, if we add bromine, chlorine, iodine, it is going to be a transformation of the halogenation. So this is how it is happening. Okay, so it is going to be attached in this way. It will be for on the side current. It's going to be attached, but they are going to be attached as far as possible from each of them. Okay, so easily react. Okay, so now you will be given few minutes to take. Why? So you will be given few minutes to take, and by the time you are taking the time, you can also go to the menti.com, please. Menti.com. Okay. Good. So now go to menti.com and copy link. I put it here, the link. There will be two Menti questions here, right? So please do it. Take the quiz faster. Yeah. So what is the type of configuration of the following molecule? What's the type? Voting is closed. Okay, I need to see it. Okay, voting is open now. Yeah, actually, uh, I throw this question the Saturday, but many of you are not here. Anyway, you can still take it. Yeah, Saturday I had a class as I announced it. But it is recorded and I have posted it there already. First, huh? Yeah, that's why I cover actually most of the Saturday. What I covered on Saturday, I covered today most of it. Yeah, there's the thing. Even this Menti question was on Saturday as well. So yeah. Please, okay. 1 minute you have. Vote faster. 1 minute. What type of configuration for the following molecule? Says trans, EZ, whatever. Faster. 40 seconds. I have only one vote so far. 30 seconds. Only 3, 4 vote so far. 20 seconds. Faster. 4 are there and 6 are here. 10. 10 seconds. 3, 2, 1, 10 votes. All right. So let's see. 4 of us says it's trans. 3 says Z. 3 say E. Now the correct is it is a Z configuration. It's not cis or trans, right? Because it is, I mean, why do you call it cis? Because of these two on the same side, but same side on that. Is it for this? No, but the thing is, it is not the same group. So there is no cis and trans, but there are two big groups attached. One is CH3. Oh, okay. Yeah. I should. Sorry, forgot. Yes. So now there is no same group on the either side or opposite side. So there is no cis and trans. But the thing is, the two big groups are attached to the other side of the carbon, double bond of the carbon. One is CH3, another is CH2OH, CH2CH3, 2CH3. It is the CH2OH has higher molecular mass than CH3 right? Oh, because oxygen is 16, so it has much higher mass. And then CH3, of course, is. So this is Z transformation configuration of this molecule. All right, so go to another, probably. Yes, if you want to go to washroom, you can. Another Menti question, right? Another Menti question is link copied. Go to menti.com or no need, just click on this link. You will directly be there. All right. You will directly be there. Just click on this link. And yes, this is the one. What is correct for this? What is correct for this? I mean, what is correct is what is the correct statement, or which is more preferable to see or to tell about this molecule. What is the name of this molecule? Yeah. What is the name of this molecule? Huh? Why alcohol? Huh? Oh, hey, yeah, good. Alcoholic group is there, but can you specifically tell the name of this alcohol? Methanol, yes. Good. So this is a methanol, and what is correct for it? 31% left. Okay, this count down 1 minute. Faster, 40 seconds, 45 seconds actually. I'm expecting another 4 votes in 30 seconds. 25 seconds. Faster. 10 seconds. Okay. So, wow, it's good that nobody goes to the electrophobic, nucleophobic thing. So, B nucleophilic, A electrophilic. Three say that A is nucleophilic, B is electrophilic. And the correct, there is no correct answer for this. Why? I didn't put the correct answer. Why? Oh, now, now, now look at it. Since there is no correct answer, I mean, I didn't put. So look at it. How do we find what is more logical? What is more logical here? This A has oxygen has 2 to 4 electron. So that means it is electrophilic. It's nucleophilic because it has electron. It wants nucleus. It is itself negative charge, so it wants positive charge. And the positive charge is in nucleus. So it is nucleophilic. A is nucleophilic and B, of course, hydrogen positive charge, so it will be electrophilic. So that is the correct answer. And I don't know why I didn't show, I forgot to put actually, that's the thing. So it will be, the correct answer is this. Yeah, the correct answer is this, A. All right. So now we'll continue to our lecture slide, to the reaction. Okay, continue to our reaction. Now, what we are going to see is some easiest way of getting Nobel Prize. How many of you want to get a Nobel? Not you? Why? Why? Why it doesn't interest you? Yeah, really, I'm going to that. That is very easy to get Nobel Prize. You will see that. See, this guy, he got Nobel. It's such a simple reaction, right? It looks simple. So, yes. You see, this is the reaction. This is the reaction this guy came up with. Yeah, this is the reaction. I think better take the laser. So this is the reaction. The bromine is going to react. The same, this reaction has been known to us for a long time. This reaction has been known to us for a long time. We knew it for the long time because you know that. Have you heard? I think I talk about it. Margarine. You know margarine. What is that? Huh? Butter, artificial butter, right? How it is produced, artificial butter? Yes, this is the reaction. It's not halogenation, it's hydration. Okay, so the hydrogen, you just put the hydrogen, the oil, of course, with some, with the help of platinum or what is it? Nickel, yeah. And then the reaction will happen into the oil turns to butter. This is the majority. So reaction has been known for us for a long time, not recently, but when we add bromine or halogen in presence of carbon tetrachloride, it produces trans product. It was not known to us that how does it happen or why does it happen? And this guy bring us this idea Yeah, George Ullah in 1994, he got the Nobel Prize, but he did the work long before, right? So in 60s, he got this work. So he found out what is the mechanism, how this thing will happen. So he proposes, and it actually works. So we do not have to worry now how this bromine or chlorine or fluorine or iodine will do the reaction, and it will produce a transport. So he came out with this product that in carbon tetrachloride, because of this solvent is non-polar, it pushes this thing. And since it is non-polar, when it is even producing carbon positive charges, carbocation, yeah, when it is even producing carbocation, since there is no polar molecule in the solvent, so it is unaffected. And later, another bromine is coming and producing and binding this carbocation and forming a trans product. So he came out with this idea or this explanation, this reaction. So this is how we are producing this trans bromo, dibromo hexane, cyclohexane, right? So this is the way. What would happen if there is no carbon tetrachloride? Not carbon tetrachloride, let's say we are putting water or methanol. All of them are carbon tetrachloride is non-polar. Water, methanol, ethanol, E are polar, right? They are polar solvent. So if we would put polar solvent, then it would be much different. The reaction, how it happens, you see now. The reaction. It's difference between them. Can you spot the difference? Can you spot the difference? Can you tell me what is the difference? Just now and the previous one. The previous one, we had dibromo or hello, right? Dibromo, difluoro, of course not fluoro, dibromo, dichloro, diiodo. But here, in this case, I am getting alcohol. In this case, I am getting alcohol, halohydrin alcohol. So this is because of this water molecule. But and water is very hard to later remove it because water is soluble and this thing is also soluble. So they will mix together in the water. So it is in dimethyl sulfoxime. It is actually done in dimethyl sulfoxime, and it is also very difficult for me to remember. So I put this note. Where is that? Dimethyl sulfoxime. It is usually it is in this type of solvent. This reaction is done without water. Okay, so and you can see that part as well. I don't know why it was supposed not to be. Anyway, how do I stop it here? Okay, so another reaction that is direct hydration. Hydration, I'm going to directly put water in it. If I put directly water in it as well, I can get the halogen out of this, alcohol out of this double bond. Out of this double bond. The thing is, it is so easy to produce alcohol from here. Right? You just put alcohol in presence of, look at the reaction and can tell me what is I need in presence of what I need to produce alcohol. What does this H plus mean? What does this H plus mean? It means acidic condition. H plus is acid, right? So why you are scared? Say that means you have to do this reaction in acidic medium. The acid is working as the acid is working as a catalyst here. So you just need a little bit of acid and then it will produce alcohol and in this form, the alcohol. Okay, so this is not a regio specific or a regio specific. It's regio specific or not? Again, Markovnikov rule. So if it is the Markovnikov rule, it is applied, it is a regio specific. So here it will be produced, more carbocation will be produced here for this reaction, or this reaction. You see that here hydrogen for both this case is equal amount of substitution, but for this case we see that this carbon, right? For this carbon we have the most substitution. One substitution here, another CH2 is attached to this carbon. And for this carbon, I have one hydrogen, of course, one hydrogen, I mean, it has 1, 2, 3 bond already. So one hydrogen is there. One hydrogen is there. And there is one CH2. So this carbon is most substituted here. So the carbocation will be formed here. And then this hydroxyl, the hydrogen is going to the more where the carbon has more hydrogen. Markovnikov rule, rich getting richer. The hydrogen is going to the carbon who has already a lot of hydrogen. So the hydrogen out of this H2O, right? Out of this H2O means hydrogen plus hydroxyl, of course. So this hydrogen is going to that carbon where there are more hydrogen already, and hydroxyl is going to the carbon where is more substitution. So this is a Markovnikov rule. Until now, what we see that we do not need to memorize the reaction. If we know the rules, we see the condition there. We are good to remember or to find out what is the product is going to be if we remember the rules. So if we remember the rule and the condition, not necessarily it will be pentene, cyclopentene, right? It's not, it can be cyclohexene or benzene or phenol or anything else. We can find what the reaction will be, right? It is not necessarily has to be this one. We can find the reaction, what will happen if the reactant, excuse my drawing. Excuse me, okay. What is happening? I cannot erase. Okay, so let me draw again if it does not allow me. I'm drawing. So if it is not the cyclopentene, if I know that it is a cyclohexene, right? It's a hexene, cyclohexene, so I can have the reaction here as well if I have this type. Or if I have a phenol or toluene, all those things, like there's a hydroxyl group here, and or there is a, let's say that here is a methyl group or anything, I can find out what will be the reaction, right? I know what will be the reaction. If I know the rules, can we? And if I ask you, or the question asked that what will be the, show the mechanism of the reaction, we can find out the mechanism because we know this is the Markovnikov rule. So the carbocation will be formed where it is more substitution already there, and that will be more stable. So yeah, that the product will be followed in that way. So this is oxymercuration. Oxymercuration, when there is mercury and acetate, oxoacetate is there, acetylation is happening. So Markovnikov rule, it is also, again, it is followed by the Markovnikov rule. It is already again followed by the Markovnikov rule, and the reaction is occurring because of this mercury oxoacetylation is there. So the mercury, since it is a heavy molecule, divalent, and it is going to attach to this more substituted carbon. This carbon is more substituted. This carbon is more substituted, so this carbocation will be formed here because it is substituted, means it has bonded with two CH3, CH2. This is the three bond it's made. Carbon, it has only one hydrogen here attached, sorry, and it has two carbon. So this is less substituted than this one. The carbocation will be formed for this carbon, and of course it is going to attach, the hydroxyl group is there. And later on, sodium borohydride is a reducing agent, which is reducing the mercury from it, right? Is reducing the mercury from it. Okay, so this is another reaction, and then hydration of hydration by hydroboration. Same thing, Markovnikov rule, but in this case, just because of this H2O2. What is H2O2? Anybody knows what is H2O2? Hydrogen peroxide, right? Hydrogen peroxide, which is a very strong oxidizing agent. So this, because of this H2O2, Markovnikov rule will be inverse. Anti-Markovnikov rule will be applied. If I just remove this part, the H2O2, it is going to have the Markovnikov rule. But when there is H2O2, it is going to be anti-Markovnikov rule. That is very important for us to remember. Anti-Markovnikov rule will be applied in this case. So I was telling, right, few minutes ago that Markovnikov rule and anti-Markovnikov rule. So this is the anti-Markovnikov rule when there's hydrogen peroxide, which is very strongly oxidizing agent. This is happening. Okay, so now another reaction is there that boron trihydride, when it is reacting with this alkene, it is producing trialkyl boron. This trialkyl boron, it is a precursor of producing alcohol. From one molecule, I can produce 3 molecules of alcohol later on if it is broken and hydrolyzed. Hydrolyzed with water. If it is given with water later on, right, reacting with water, so it will take 3 moles of water to produce 3 oxide. So it will be broken from here. It will be broken from this part. Hydrogen will be attached to this boron, 3 hydrogen, and 3 hydroxyl will be attached to this alkyl group. 1 hydroxyl is there, 1 hydroxyl is there. So all 3 hydroxyl will be attached, and then 3 alcohol molecule can be produced. So this is a very useful, helpful, efficient process of producing alcohol, mass production of alcohol. Mechanism of hydroboration. It is, boron is less electrophilic. sorry, yeah, boron does not require that much. So it will move towards the carbon which has less substitution. So the boron is feeling attached to, so this carbon, because less substitution it has. It has one hydrogen attached to it. That means, and this carbon has, of course, this group, and there is another CH2 group, of course, here, and there is another CH group. So this carbon is the most substituted. So boron does not feel attached to this substitute because boron is less electronegative, electrophilic. So it will be attached to this, and then like that, it will produce a hydroxyl or alcohol molecule in that way, just because that the way that we have done. This is not a cyclic alcohol or cyclic product. This is not a cyclic. This is not a cyclic way. Alkane, but this is a cyclic alkane. We need to remember both of these mechanism, right? Not necessarily it will be for this exact molecule. Maybe it's different molecule, but the reaction mechanism is same. So you can show the reaction mechanism. Hydroylation of the alkene. This is even, this guy again got the Nobel Prize in 2001. He was working on this organic stereoselectivity. Stereoselectivity means the isomer you want to produce, because the same carbon, same alcohol, when it is a trans, like here, when there is hydroxyl, group is here, or when the hydroxyl group is there, what is the difference? Is there any difference? Or if the hydroxyl group is there, will there be any difference? What do you think? Is there difference? Is there any difference? I put the hydroxyl group here. I put this hydroxyl group there. Is there any difference? Huh? Yes or no? A binary option you have. Yes or no? Yes. Why is the difference? Because this is called stereoselectivity, specificity, right? This hydroxyl group, the characteristic of this type of hydroxy product is much different than what we have now here. So if a hydroxyl group is here, the characteristic of this product will be much different than it is here, or from another person, another space. But since we are talking about heat, let me tell you one thing, that first need to erase. Okay. Yes, and then here. So in respect, I start counting from here, right? 1, 2, 3, 4, 5, and 6. Right? 6 here. So this hydroxyl group is at 2 position. If I put the hydroxyl group in this here and remove it from here, now I count from this way, right? I count from this way, so that I get the substitution earliest number possible. We have seen this rule, nomenclature, if you have remembered. So in this case, it is the same thing. Similarly, if I have a hydroxyl at 3 position, here, it is as it is in 5 position. As it is in 5 position, right? So same thing. And of course, 6 cannot be, 6 is always the same. So that is why sometimes if it is an aromatic compound, we will see later on, aromatic compound, if it is an aromatic compound, let me just quickly draw it. If it is an aromatic compound, that means it has a double bond in between, okay? It has a double bond in between. So what we do is, we do not put 1, 2, 3, 4. We put ortho, meta, and para notation. So in respect to this group, it is in ortho. The number 1 position is ortho, number 2 position is meta, and number 3 position is para. So this ortho, both sides it will be ortho. If there is hydroxyl, it will be ortho as well. In this position, it will be meta as well. And para, of course, is para is para. Ortho, meta, and para. These 3 notation we will see later on when we study that or aromatic compound. All right. Anyway, so the hydroxyl, that is called stereoselectivity. Selectivity. And this guy, who is that? This guy, he got this Nobel Prize in 2001. He, of course, not only this, but he worked a lot on this type of reaction, stereoselectivity. And one of his things was this, that osmium tetroxide, when we add the osmium tetroxide to this alkene, the osmium tetroxide will force it to produce a diol. That means hydroxyl group will be attached to 2 adjacent carbon of the double bond, and they will produce the diol, and it will be a cis product. It will be a cis product just because we are using osmium tetroxide in presence of sodium bisulfite. This is a very interesting reaction, but another interesting characteristic for this reaction is this type, this osmium tetroxide and sodium bisulfite, they are the precursor catalyst for this reaction is occurring. Interesting thing is this catalyst is playing the part first. Only water is coming at the last stage. When the field is prepared, only then water is added to the reaction to produce the final product. So this is another interesting thing for this reaction. Usually what we do, we add the reactant first and also a little bit of catalyst so that the reaction will occur. But for this case, you see that the reactant, the catalyst is there already, and then the reactant is coming after the field has been produced. Okay, so this is mostly 87% or 90% of the product will be a cis transformation. But osmium tetroxide is a very, very toxic product. It's a very, very toxic. Epoxidation, we will see it later, and we have still time, so we can finish the epoxidation. This is another very interesting, very useful, in fact, the product, epoxide. Or have you seen the epoxy resins or epoxy, what do you call it? The epoxy glue, right? Adhesive, epoxy adhesive. No? All this leather, your shoes, all these things that we use the epoxy glue. This epoxy glue is because of this. So this type of product usually called it epoxy. This is the epoxy, it is called when oxygen is attached to this 2 carbon simultaneously, because oxygen can form 2 bonds. So it will be epoxy. In that way, you call it epoxy. It's very similar to the electrophilic addition of reaction, has a few twists. We'll see it later. So this cleavage, oxidative cleavage, it will form first when the ozone and zinc in presence of acid is used. So it is breaking this part, and then aldehyde and ketone both are being produced. We have seen it before, the aldehyde and ketone, we know that. And then it is carboxylic acid and ketone is being produced. So it depends on this. Because of this zinc, it is aldehyde. Because of this peroxide, it is a carboxylic acid. So this is an interesting thing that we should, and the reaction mechanism is, of course, we can see it, and nothing much to talk about. So the next time we will talk about the aromatic compound next class, and alkynes. Alkynes, there is nothing much to talk about alkynes, and there is not many things we will talk. So we will talk about the aromatic compound. Hopefully we can finish the aromatic compound next class. All right, so now another just one last Menti question for you. Last one. And it is a very easy one. Yeah. Okay. Go to Menti. No need to go to Menti. I'll share the link. The link is here, and you will have some fun time looking at this. Right? Yes, here. Which one has the more polar bonds? Oh, did I ask this question before? Did I? Okay. So go to the another one. Copy link. Paste it here. Just hold on here. Hello. Hello. Yeah. Yeah. Have you? Which one is more in basicity? Oh, we haven't talked about it. Sorry. Next class. Next, after the next thing, we will talk. Anyway, so yeah. I think is today I'm done. It's done. So all right, so I'll see you next class. That will be tomorrow for the lab. And please bring your manual, come prepared. And also, please, what? Yeah, see you tomorrow. Anyone has any question before we stop it? No, no question. Okay. All right. Yeah. Yeah. Ask the question, please.